So I thought it's better for me to derive this equation for you. So last time we defined the so-called wave impedance. So wave impedance is basically the total. So the wave impedance, ZD, or Z as a function of distance along the transmission line, including the load impedance, is the total voltage as a function of space divided by the total current as a function of space. So this is J beta D plus gamma B exponential negative J beta D. And then the total current divided by Z0, but the same thing, but having a minus sign. If you still remember, the reverse current is having a negative sign. The forward voltage amplitude cancels out. So now we have this expression. Right? We're looking for an impedance. So indeed, the voltage is cancelled out. So now the characteristic impedance is now in the denominator. Okay? And then it's multiplied by some kind of complex value. So in order to derive the equation marked by the yellow on the PowerPoint, we only need to insert the expression for voltage reflection coefficient. Gamma V is nothing more than Z load minus 1, Z load plus 1. So here, the load impedance is normalized by the characteristic impedance. Okay? So we only have to replace gamma V by this expression. Okay? So let's do the procedure. So after I finish all the derivation, the teaching assistant will take a picture for you. And at the same time, our Center for Teaching and Learning Development is working very hard. So they are trying to ensure all the classes will be edited within the week. Right? So if you have trouble jotting down the notes, we have photo, and we will have a very clear edited version of video by the end of this week. Okay, so I need to thank all the staffs here. So at this time, all I have to do is normalize, right? I can multiply everything by this normalized load impedance plus 1. So that is minus. Remember, here you have a minus. Okay, so now let's collect terms. The terms having the normalized load impedance and the ones not having the load impedance. So Z load normalized will have J beta D and minus negative J beta D and plus exponential J beta D plus, right, plus, okay, and minus exponential negative J beta. On the denominator, I have Z load now I have a plus, and then plus. Okay, so when we look at exponential j term plus its complex conjugate, I have 2 times the real part. The reason is exponential j theta, it's called Euler's identity, is cosine theta plus j sine theta. Right? This is something we learned from maybe high school. You're all smart, so your high school level is very high. Okay. Right? So the top part, this is becoming 2 times the real part. The real part is cosine beta d. And this one, this minus is complex conjugate, so now you have 2 times the imaginary part. So 2 times j imaginary part and sine theta. Alright, so at this moment, all we have to do is divide the top, the numerator and denominator by cosine beta d, so we can have tangent. Right, so in the end, this is z0 normalized load plus, and then we can divide by 2, right? 2 cancels out. By j tangent beta d, and then it's the real part 1 plus j z load normalized tangent beta d. Okay, let's compare to what I wrote down in the PowerPoint for you. Hopefully I didn't make any mistake. Okay, it reads the same. Okay. So this is really nothing new. It's something you want to do live. You want to spend maybe 10 minutes. And then in the future, I mean afterwards, you can simply use this formula so you can quickly understand what is the effective impedance, right? We started from the load, right? We understood the reflection coefficient, and then we walk back to our input, and then we look into the entire transmission line plus the load. And then we can use this simplified notation to express the entire transmission line, including the load, as an effective wave impedance. Okay? So remember, the wave impedance will definitely be a function of distance. But the characteristic impedance, Z0 is a constant, which is defined by your transmission line. Okay? So you have to pay special attention to being able to differentiate the two. Characteristic impedance is a constant. It's provided by the transmission line. But the wave impedance is the total voltage as a function of space divided by the total current as a function of space. So it will be position dependent. It is a function of D. Okay? Alright, so I went over the slide quite quickly last Wednesday, so I want to spend some more time on this. Right? So now we have formally derived the expression for the wave impedance. As I said, our knowledge to the transmission line gradually increased. We know that on a transmission line with some kind of load, we have forward propagating wave and backward propagating waves. So we have 2 waves. And once we have the 2 waves, it will create some kind of standing wave, which we explained on Wednesday as well. Okay. So now, we want to solve for everything, so the idea is we know the reflection coefficient, so we know how strong the backward propagating wave is at this point, at where the transmission line is connected to the load, right? And then the strategy is we walk back until we meet the input point. And then we look to the right. And then we say, this is effectively a load. And that load can be defined as my input impedance, right? The effective impedance that I see when I stand at the input point and looking to the right. And looking to the right means including everything. So now I have the power to write down the transmission line, including my load, as a single effective impedance. Once I can do that, I can write down my input voltage. That's something we learned for voltage division rule, right? So we know our input source voltage is Vg, and I have my intrinsic generator impedance, and now I have my entire effective input impedance. So the power distributed over this input impedance is Zg plus Zin, and then it's proportional to how strong or how big my input impedance is, right? So this is my Vin. But this Vin, at the same time, I already know my expression for the total voltage everywhere on the transmission. So that is V total at L, right? What is L? L is my total length of my transmission line. So this is equal to V0 plus. Finally, this is the only last parameter we want to solve, right? V0 plus. So somehow I can relate this unknown variable, the very last unknown, to everything I already know. So let's check. This is given, right? I have to know my generator voltage phasor, and Zin known, generator intrinsic impedance known. This is known. I know my length. I know my transmission line. Knowing my transmission line means I know beta, right? I know the effective wavelength. I know beta. And I know my load. Once I know my load impedance, I know my reflection coefficient. So the only thing unknown here can finally be solved. Okay, so let's come back to the PowerPoint. So this is again just to repeat what I wrote on the blackboard. Okay, so this my input voltage is determined through the voltage division, and then that voltage is my total voltage phasor at the distance of L equals to that. So finally we have the proper mathematical formulation for the forward propagating voltage amplitude. V0 plus is that whole bunch of mathematical formula. So this is only to conclude up to now that indeed, once we provide you the operational frequency, once we provide you the transmission line parameters, right? You know gamma, alpha plus j beta, you know the effective wavelength, and once we provide you the connected load impedance, basically you know everything. You know the voltage and current as a function of space on the transmission line everywhere. Okay, so everything can be solved. so you understand what's going on the transmission. So that's a quick summary to the mathematical derivation, and starting from the next minute, we are going to understand about transmission line with certain load in more details. I would say these are more specific cases, right? So up to now, we have derived all the general solution forms, and then we're going to look into specific or particular cases, right? So finally, we spent so many hours, so we now know everything. So special cases, again, over the weekend, I have to thank one of the students who wrote me an email asking 2 questions. So the first question was, we talked about lossless transmission lines, right? We made the assumption the transmission line is lossless, and then we defined the reflection coefficient, right? So his question was, does the definition of the reflection coefficient still holds, even though the transmission line is lossy? So the answer is yes, it will hold, because the reflection coefficient is the reflection at the load point, okay? So basically, if you have loss, the reflection coefficient definition still holds. It's only through the teaching we want to make everything simplified, okay? So having the loss or not is not really going to affect the derivation results, but it's going to make things more complicated, okay? So even though we have loss, all you have to do is, well, you include right, everything. You just add the loss term back, and you will see how messy it becomes. When you add the loss term back, all these derivations are slightly more complicated, but the most complication will be in the standing wave ratio. Because the standing wave ratio, the amplitude, once you include loss, it's very hard to write out the analytical equation, okay? So, simple answer, it will hold. Everything I'm teaching now are still valid, even though we have loss. But usually, as professors are really lazy, we just say that loss is not there, okay? And the second question is a very nice one. So he was also focusing on the reflection coefficient and the standing wave. So he was trying to relate to the rope wave that everybody here learned during junior high school, right? So if you have a rope attached to the end of a wall and you try to just do this, and you will create a standing wave. This is exactly identical. Okay, exactly identical. It's just a different wave. But having the standing wave means you have an input wave and you have a partially reflected wave. So you will have standing. Okay, so I have to thank the student for writing the email, asking the question over the weekend. So let's move on. So the special cases of lossless transmission lines. So now the special cases are more pronounced if we don't have loss. But again, if you have loss, if you want to include loss, just include it. It doesn't really make a lot of difference. So the first case we're going to look into is short-circuited. Okay, the second one is open-circuited, half wave, quarter wave, and matched. So I am trying to divide or classify the special cases into 5 different types. The first one is shorted. Okay, shorted means I have a long transmission line, and at the end, they are connected directly by another wire. The formal definition of shorting, shoto, right? Shoto. Shoto is Japanese or Taiwanese, I don't know. Short, okay? You want to just short it. So by shorting your transmission line, what are you trying to enforce? If you're really good at math, By shortening the transmission line, you are forcing the boundary condition. Voltage at Z equals 0 or D equals 0 is forced to be 0. Right? By definition, you cannot have voltage. But once your voltage is 0, what happens to your current? Think about it. As I unfold, think about it. By short definition is voltage has to be 0 at that point. But what happens to the current? Right? This is something we know already. We know how to write the total voltage phasor as a function of space, and we also know how to write it down for the current phasor as well. By short, gamma V is now -1, right? Because your load impedance, ZL, is 0. So your reflection coefficient is -1. So that's why here, for the voltage, you have a -1. -1 times exponential negative j beta d. So this is going to give you some kind of voltage phasor, total voltage phasor as a function of space. Now for sine beta d, d equals to 0, sine is 0. So indeed, when you short circuit your transmission line, at the short circuit position, d equals to 0, you cannot have voltage. Right? So voltage has to be 0. What happens to the current? Think about it. Usually, our understanding is, well, if a position is not having voltage, your current is voltage divided by impedance, right? So 0 divided by something is still 0. But look at the expression. Because gamma V, the reflection coefficient, is now -1, so the current total phasor is now having a plus. So exponential j beta d plus its complex conjugate is now having cosine term, cosine beta d. When d equals to 0, cosine of 0 equals to 1. So this means even though at the termination you short circuit the transmission line, you don't have allowed voltage, it will be 0 forever. That point cannot have a voltage value other than 0. But the current is actually picking up its maximum value. So this is something you have to understand. This is very different, right? Because usually you think, well, voltage divided by impedance gives you current. But in this case, 0 divided by something gives you maximum. Is it really possible? It's possible because we're looking at the result of standing. I don't know whether I want to go into the details, but gamma V equals -1. Think about it. Gamma V equals -1. So the total voltage is your input voltage 1 minus 1, right? At d equals to 0. So 1 minus 1. Ideally, you want to add the two. But the reflected wave in terms of voltage is -1, so it cancels out. So if you want to look into the definition of gamma V, why am I always adding this V? No one asked me about this question. The reflection coefficient can be defined as V0 negative to V0 plus. Okay. So by this, reflection coefficient is referenced to the voltage. You can also try to define the reflection coefficient in terms of the current amplitude. You can also have this, I0 minus I0 plus. That's also possible. Go back home. You're already at home. Go back after the class and try to derive everything using the definition of gamma I as defined by the reflected current amplitude to the input current amplitude. You will see that in this case, when the short-circuited transmission line, your gamma V is -1, but gamma I is 1. So you will have the maximum value of current at the short-circuited termination.